Good evening and welcome to Science Café at Oklahoma State University Library. Tonight we are joined by Nate Lannan. Nate received a BS degree in electrical engineering and a BS degree in computer engineering from the University of Kentucky in 2010. He's currently pursuing a PhD in electrical engineering at Oklahoma State University. Nate is an assistant professor of practice at Oklahoma State University and teaches capstone design, software engineering, and digital logic design. He is the faculty advisor for Cyclone Cowboys, a student organization focused on wind energy research and the collegiate wind competition. Beyond wind energy, his research interests include human motion analysis, computer vision, machine learning, audio signals, and video game development. Tonight, Nate will talk to us about his work with wind energy and undergraduate research.
Alrighty. Hello, everybody. I'm going to kind of go into a little bit more detail about myself, just to give you a little background on what I do and talk a little bit about my current research beyond wind energy and kind of what led me into wind energy. So as Kevin stated, I got my bachelor's at the University of Kentucky and my master's here at Oklahoma State, and I'm ABD here at Oklahoma State for my PhD, so any day now, hopefully. So outside of academia, my experience has been as a research engineer with the Unmanned Systems Research Institute here at OSU, doing flight controllers for drones and a lot of actual weather analysis using drones and mounting anemometers to drones, things of that nature. Before that, I worked at Lexmark in Kentucky as a security firmware engineer. And before that, I worked with the Smithsonian Institution as an audio engineer. So currently, what I'm getting my PhD in, and my current research, as it were, is in human motion enhancement. And it's kind of a niche field that uses depth sensors to locate the joints in the human body. Normally, when we think of human pose analysis and human pose research, we think of mocap machines, and with CGI and video games and movies, those sorts of things, we use mocap machines because they're highly accurate. However, there are some disadvantages with them in that they are you're confined to a certain space where the array of cameras are, IR cameras are, and you have to have attached markers on your body for it. My research is in using depth sensors, which are completely free of markers and completely free of a confined environment. However, they're not as accurate as mocap machines. So what I'm doing is I'm taking the data from the depth sensors. You can see the difference here between a mocap machine and data gathered from a depth sensor. And I'm using deep learning to try to clean up this skeleton so that we can more accurately represent the movement that we get with a mocap machine. The way I do that is with convolutional autoencoder, and basically what that does is it takes a very large multi-dimensional space and kind of crushes it down into a smaller space and kind of boils whatever you're doing down to its essentials so that you can have a boiled down version of what you're wanting to do. So you train it on clean mocap data so that it can learn what we call a human motion manifold for human motion. And then when you give it noisy signal, all it has learned is this manifold, and so it has no way of understanding the noise, and it just gets rid of the noise. So my research uses the convolutional autoencoder as well as a Tobit Kalman filter, which is a special type of Kalman filter that does well with occlusion because of some thresholds that it uses. I won't go into technical details because that's not really what my talk is aimed at. But I just kind of wanted to show you some of my current research and show you the results that I have. So this is some noisy data that I am feeding through the convolutional autoencoder, the TKF assisted autoencoder, and the results of the output of my autoencoder in comparison to a mocap reference that was taken at the same time as the noisy data. So you see it cleans up the noisy data and gets a lot closer to what we're aiming for with the mocap reference. So beyond that, my work at USRI really kind of got me started with wind, kind of indirectly. I didn't really expect for it to happen. But I had a project with that group called Cloud Map, where is a group of universities that got together to do weather analysis with drones. And you can't really see all that great, but on top of this drone here is mounted a anemometer. And we flew these drones up in the air to gather wind and weather data, because there's kind of a gap between high altitude airplane data that we get from the weather and helicopters and low altitude data that we gather here on the ground. And so we were trying to, and continuing, I'm not part of it anymore, but continuing to kind of map that space between the ground and the airplanes. So this is where I kind of got my start with wind, and actually started talking to Dr. Jamie Jacob, who's the head of USRI, about being able to use drones to analyze wind eddies and wind interference between wind turbines, and we were kind of fascinated by that idea, and that's kind of where this all got started. Over here are some other projects that I worked on at USRI. This first one is a methane sensing drone that flew over methane fields and would try to search for leaks so that humans would not have to go in and fix the leaks and breathe in the methane. And then this one down here is a deep learning network that was an object recognizer that recognized drones over any other sort of object. So that was kind of where I got my start. I got my start in my undergrad, though, for renewables with my senior design project. Ironically enough, I've come full circle. This senior design project was a solar-powered robot that went to competition for IEEE. So this is pretty interesting that this is where I started, and now I'm leading an undergrad team to go to competition for renewables, which is kind of cool. So this robot was powered. We couldn't have battery powered. Couldn't have any battery power. We couldn't have any sort of power up station or anything. It all had to be powered from a solar panel. This is a preliminary test, so we don't really see the panel that we ended up having on top of it. And then all of our storage was done with supercapacitors instead of batteries. So it would, as it goes around this circle, you'll see a light on this track. And at the start of our run, we would power up with this light and our solar panels, charge up the supercapacitor array, right there's our light, and then run this obstacle course. And it was a competition for IEEE where a whole bunch of universities got together with various different designs. So I've kind of come full circle and come to the collegiate wind competition. I started out exploring wind turbines with that idea of can we somehow analyze the interference between various turbines. And I started out with a senior design team to build a wind turbine test bed that did pretty well, but I found out about this collegiate wind competition, and the aspects of it were so enticing that it was a no-brainer to go with this rather than continue on my path, because there were so many aspects of this competition that drove like an engine for year-to-year expansion in the university, which is really nice because it's caught on like wildfire and made my life really busy in a good way. This picture over here on the left is last year's wind competition. I'm over here in here somewhere, teeny tiny. This is a picture from inside of one of the wind tunnels at the competition. So Cyclone Cowboys is now on its second year. We started it up to take part in this competition. Myself and Professor Laura Southern, who's in the audience today. Thank you very much. So we started this up last year, and our first year we were one of the lucky teams to make it into the finals, which is kind of an anomaly. I was talking to a lot of the other competitors when we went to competition, and they kept saying, "You're a first-year competitor and you made it into the finals. That's pretty impressive." Usually they have a half-year downsizing event where they go from about 30 teams down to about 13, and those that don't make it in usually show up to the competition as a learn-along, aren't actually scored, but can participate. So we were fully expecting to be a learn-along, and we made it in, and was really proud of all the students. They really worked hard to get in. So that is that team, our inaugural team, and this is this year's team. This year's team has taken what last year's team did and kind of run with it, and I'll kind of explain the troubles we ran into at competition and what we're trying to do to solve that, and all the aspects of how we can improve and how we can grow and get bigger and better. I don't want to take all the credit for this by any means. This is a huge interdisciplinary project. It is involvement from so many different advisors, so many different departments, because the competition has so many aspects to it. This year we partnered with Kathy Jackson at Northern Oklahoma College, and super happy we did, because Kathy has a ton of experience with wind turbines, with wind turbine education, with outreach, and she's really helped us bolster our program. Not only are we a student organization that anyone can join, and we really want to encourage everyone, no matter what your background is, you don't need an engineering background to do this, and in fact it's better if you don't, because we need all the aspects that other schools can provide for us. So not only are we a student organization, but we have members from the Electrical and Computer Engineering School, Mechanical and Aerospace, Electrical Engineering and Technology, Mechanical Engineering Technology, Civil and Environmental Engineering, and Industrial Engineering and Management, as well as a few other schools in our student organization. But this isn't enough. I want more. I'm greedy, right? Because there is so much involved in this project. Not only do we have the engineering aspects of fabrication, electrical design and controls, mechanical design, fluid dynamics, and aerospace design, but we also have a whole bunch of other stuff: graphical and design and marketing, business and finance, and outreach and education. So we would love to see new members, especially freshmen, who could get involved early and continue on throughout the years in schools such as education, business, graphic design, all this stuff we would love to see. So we really want to expand, and we want to expand beyond engineering. So that's kind of a background of what Cyclone Cowboys is. I'm going to give just a quick overview, very thumbnail sketch of wind power and how it works, and kind of just to give you a background in the technology, so that when I talk about things about the turbine, you understand what I'm talking about. So the underlying scientific phenomena that we use that creates power for us in the wind turbine is Faraday's law. And Faraday's law is that old classroom experiment that you may have done in high school or junior high, where you passed a magnet through a coil and generated electricity, right? So that is what all this is based on. Excuse me. And from that, we can build AC generators, and we can build DC generators. The way the AC generator works is we have a electromagnet in the center of basically a stator, or just a circle, and it spins. And at each of these stations of the stator, we have electrical windings that generates AC current. That when I say AC, it fluctuates between a positive flow and a negative flow, because the positive end of the magnet will pass through a coil for an instant, and then the southern end of the magnet will pass the coil after that, and you'll have a positive flow and then a negative flow and then a positive flow and a negative flow. And we have, in this case, a three-phase AC generator, where we have three windings basically that will all be slightly out of phase with each other. This will be at its peak generation when this north pole passes by this C, and then as it passes by B, it will then generate the peak of the B. So they're all slightly out of phase. They're all peaking at a different time. So that's three-phase AC. DC is used with brushes, and these brushes are connected to rings, so that when you have a wire, let's say hoop, this is a very simplified version, but as this hoop spins inside this magnet, one side of it will generate positive flow next to the north side of the magnet, and then the other side will generate the positive flow on the north side of the magnet. But the thing is, this slip ring here swaps which side of this coil are connected to your load at each time. So as the coil changes direction, the sides of the circuit are swapped, so that you're always getting the positive peak and always getting positive flow of energy through the brush DC. Most of your big generators and your big wind turbines are going to be three-phase AC turbines, and basically that's what we have in competition. It's a brushless DC motor, but it has phases like AC, so we treat it like AC. There are two main types of turbine. We have a horizontal axis, which most people are familiar with, you see out in the fields, and then we have vertical axis. Vertical axis turbines are a lot less refined, or I don't want to say refined, but are a lot less, the design is more in flux. You see a lot of different variations of vertical axis turbines than large horizontal axis turbines. We have a pretty good understanding of what makes a really good horizontal axis turbine, which is why we see very homogeneous designs across the United States for horizontal axis. We have designed a horizontal axis turbine here. This is our turbine from last year. However, it's not, we've discussed doing vertical axis at competition in the past, and it may be something that we do in the future. The benefits are that you really don't have to worry about getting the turbine to face the direction of the wind. However, the slowing down of the turbine is a little bit more complicated since you don't really, most of the vertical designs don't have easily adjustable pitch. We lost one of the monitors. And so you have to do it all in a braked system, which you'll find out later in my talk why we're kind of trying to steer away from a braked system. So when you connect these things to the power grid, you want to match frequencies of the power that's coming out. This is AC, so think of a sine wave, positive and negative flow. The frequency is how fast those humps go through a point in time. So we want to match that frequency, and there's kind of two ways to go about that. One is using a gearbox inside of the wind power nacelle, and another is direct drive, where we don't have a gearbox, but we are instead modifying how many of these connections we have in our stator, so that it modifies how many positive peaks we have in our AC wave. We currently are going with direct drive in our designs. However, if we wanted to, we could try to get more power output, or the way we would use it, it would be to use a gearbox to try to match the torque of our generator with the speed that we want our blades to run at, right? So if we wanted our blades to run at a slower speed, but we wanted more of the generator to spin faster for whatever reason, then we could incorporate a gearbox into our turbine design. The other things that are general aspects of a turbine, your run-of-the-mill turbine, you generally have a yaw so that the turbine can turn and face the wind. This is the yaw. In our turbine, we have a passive yaw, which is just based on this bearing here, this 360-degree bearing, and a tail that catches the wind, so that when the wind blows, this tail naturally wants to line with the wind, and this bearing allows it to then rotate. You can have control for that, and most of your giant turbines out there have a control system to control the yaw to face the turbine in the correct position of the wind. Then we have pitch control, which actually controls the pitch of your blades, right? So if you think of how wind hits a blade, if you have the wind hitting it just directly flat like this, you're not going to get much spin, and you're going to get a lot of force on the turbine itself. If you have your blade like this, you're not going to get much turn either. The wind's just going to blow right on past it, right? So you want a pitch to your blade, and that really is going to control how fast you're spinning. So if you want to stop your turbine, then you can face it directly perpendicular to the wind or parallel to the wind, and the wind will just pass right on through the blade. And you'll see a lot of times when you look at turbines out in fields and stuff, those that are shut down may have a slight turn to them, right? Very slow turn. That's because they're not completely braked. They don't have an aggressive brake on them. They're just they have the pitch is set such that it's not catching the wind, and it has just a very minor turn to it. Other aspects of wind turbines, a wind vane that tells you which direction is basically a sensor that's telling you what the direction of the wind is, so that you can adjust your yaw. Your controller, which controls the yaw and the pitch, and the brake. In these big systems, you have brakes to actually brake the system if you need to, and an anemometer, just like the anemometer that I had attached to that drone in the previous slide, tells you your wind speed, right? So if we're getting into a dangerous wind speed in storm conditions, we need to adjust our pitch so that we're not turning the turbine and brake it so that we're not doing any damage to the turbine. Excuse me. So those are the main aspects of a wind turbine. The turbines that you see out in the world, the three main ones that you'll see are turbines that exist on land, which I'm sure you're familiar with, offshore turbines, which we're really concentrating on for the wind competition, and distributed systems, things like out in front of Endeavour that are used to just power small things, maybe lights, maybe traffic lights, maybe something out and about in a neighborhood. Maybe your neighbor has a turbine that runs as garage lights or something like that. It's kind of a distributed system. But we're really centering on offshore because that's kind of the future as we see it, right? Because we don't have to take up land acreage, and we can get it offshore where the wind is consistent, and it's way away from people. People don't have it in their backyards. They're not complaining about humming or anything of that nature. However, we have to be mindful of aquatic life, avian life, all these sorts of things. We have to really kind of concentrate on our footprint environmentally, and how we set these things up and how we decommission them, because they don't last forever, which is one of the major challenges with wind turbines is the reusability of them, that when they get to a certain age, they become structurally unsound, and so they have to be decommissioned, and you have to take them apart and replace them with newer parts. So just some statistics to kind of get you aware of how much wind is on the rise, especially in Oklahoma. Renewable resources account for 47%, this is from 2022, of Oklahoma's total in-state electricity generation. Almost half is renewables. And of that renewables, 93% is wind energy, right? So this is big, not only really good, but is big business right now. So there is a lot of interest from energy companies to adopt wind power. Just to kind of put that point home, this is our team here from last year talking to President Shrum and the U.S. Secretary of Energy, Jennifer Granholm. She came to visit, and it's very big. Wind power is very big and is getting a lot of attention. All right. So with that background in wind energy, if anybody has any questions too, I encourage you to interrupt me and raise your hand, anything of that nature. I'm not one that shies away from people interrupting me. So with that background, I just want to highlight the collegiate wind competition and our team, right? So the collegiate wind competition is a competition that's put on by the Department of Energy and NREL in Colorado Boulder. And it's been going on for, I want to say, between 10 and 15 years now. I can't remember exactly what the number is, but about 10 to 15 years. So there are three aspects to this competition. There's turbine design, wind farm design, which is a virtual wind farm that we design, but we go through all the steps of designing an actual wind turbine and figuring out the costs of buying actual large wind turbines, figuring out how we would actually network into the power grid for the neighboring communities, and our outreach component. So there's like those three big aspects of this competition. So the first one I'm going to talk about is the turbine design. How this is run is it's a mock-up of an offshore wind turbine. We have a wind tunnel that has an opening in this one end here, where there is a coupler that connects to your competition turbine, and then that coupler connects down to your anchor system. And your anchor system goes into this water and sand tank down on the bottom underneath the wind tunnel. And not only are we testing our electrical output of our wind turbine, but we're also testing the ability of our anchor to stay put under high wind conditions. So really we are taking a look at two very important aspects of offshore wind turbine design. And we want, not only do we want a stable RPM, which is the rotations per minute of our blades, at various different speeds. We want our turbine to be able to control how fast it's turning and give us stable power output for all of the speeds that we run at. So they test the turbines under a basic operation conditions where they're blowing wind at us from 5 meters per second to 14 meters per second. And they want to see us turn on right at 5 meters per second. So very, very low wind speed cut-in, what they call cut-in, where when you start turning is the point at which you're called cut-in. They want us to start generating power right at 5 meters per second and maintain consistency all the way to 14 meters per second. And then from there, they do basically a stress test where they test us from speeds of 14 meters per second all the way up to 22 meters per second, which is significant. And they want to see the turbine be able to withstand those speeds and not and the anchor hold so that we don't go out of tolerance. There's a hole in this wind tunnel, and if the wind turbine knocks against the back of the hole, you're out of the competition, right? So you gain all the points up until that point where you fail and hit the back, but the ideal situation is that you won't fail and you stay within tolerance of the opening of that wind tunnel. So this is our design from last year, and this is a stress test we were doing with our blades to make sure they weren't going to break up at high wind speed. We are actually treating our generator as a motor and driving it with an ESC to test our blades and make sure that they are not going to break up in the wind tunnel, because we had a few blades break up in the wind tunnel here on campus, and it was not fun. So that this design is pretty much the finalized design that ended up going to competition. I don't have the exact setup that is in that picture because, as we'll see in subsequent slides, at competition, our brake clamped down and ripped apart a bunch of stuff, which is part of the reason why we're making some design changes this year. So that here, I'll just talk a little bit about the design and how it works. Of course, we have the fin for the yaw, the passive yaw system, the nose and the blades, the drive shaft here that is connected to our generator, which is being driven electrically by the CSC. This servo that is connected to a braking system here, and it is a disc braking system like you would see in a car, or some of your newer bikes have disc braking systems, where our microcontroller inside here, when it senses that our turbine is spinning too fast, would pull this servo and clamp down on the brake. Right? And how it senses how fast this thing is moving is with something called a Hall effect sensor. And it's just a magnet that passes past a sensor and counts the amount of rotations that you have, right? I think that the most common Hall effect sensors you might see are on bicycles. If you want to ride your bike and find out how fast you're going, they have like a magnet that's connected to the wheel and then the chassis of the bike. And as that one magnet passes past the other one, it generates electrical signal and can actually count up how many times that wheel has rotated. So basically the same concept inside of the turbine here, and we built the Hall effect sensor ourselves from scratch with a very tiny magnet and a actually very tiny sensor. So that's how the basic operation of the turbine works. It worked last year. This is our anchoring system, and you can see that we are driving the anchoring system into the water and sand mixture, getting it ready to go into the wind turbine. And we're not allowed to get our hands in there. We're not allowed to disturb the sand with anything other than that anchor. So we can use tools. Here we have like a pipe that we're using to drive our anchor into that sand, and our anchor design is basically a scoop at that point. It scoops underneath the sand and locks into the sand, getting all the weight of that sand and water on the anchor so that it holds. This is our test at the competition. That's us in the wind tunnel actually spinning. And this is our power curve as it's being analyzed by the competition organizers, showing our RPM and our power output and all of that. So what went wrong was we had a twofold problem. Usually problems come in multiples, right? Our twofold problem was that our disc brake was too aggressive. It was too good. It was able to just stop this thing on a dime. But we have all these torsion forces on this drive shaft, which is actually not just a single drive shaft, but two drive shafts that are connected with the disc brake in the center. And when it stops on a dime, that thing just comes apart, right? And the other problem that we had was our Hall effect sensor was outputting erroneous data at certain points. It would be fine and giving us good RPM values for a long period of time, then every so once in a while it would just output something astronomical like 9 million, right? And then the microcontroller would say, whoa, we got to slow down big time, and it would just clamp down on that brake, and when it did that, it just ripped the whole thing up. So when this happened, we were doing our stress testing, and we had reached all the way to the end of the 22 meters per second of our stress testing, and right at that point, everything failed all at once. The Hall effect sensor shot up into an astronomical value. The brake clamped down, and because it clamped down so hard, the blades stopped. The wind pushed the blades. Our anchor failed. We hit the back, and all of our electronics and everything got completely torn up inside of our turbine. So, how do we fix this, right? This is our plan this semester. We are going with a brakeless system that instead of static blades, you'll notice that our blades from the previous semester were not able to do what I was talking about, right? Being able to change the pitch to slow down. They were just static at a certain angle. So we were scared of doing that because we thought, well, that's way too complicated for us just starting out. But we discovered in talking to the teams at competition that we could just use an RC helicopter pitch system. So we've designed a pitch system with a linear actuator that pushes a swash plate and actually rotates all these blades together. And so we can, without a brake, slow down to the point of stopping within the rules. The rules say 5% of our actual top speed, or 5% of our actual startup speed, that we can rotate these and slow down to the point where we're at a stop without actually having to use a brake, and then we can use a single drive shaft that is at much less risk of being demolished. And then along with that, we have discovered another generator that has an internal Hall effect sensor that's actually built in and completely reliable, very, very well designed generator. So those are the two things that we're tackling to address the problems that we had at competition. So the second aspect of the competition, wind farm design, we were initially building a wind farm in the Gulf of Mexico for competition, and this is our lease block analysis, right? So we actually have to analyze all of the shipping lanes in the ocean, all of the, if there's any oil rigs, any pipelines in the ground, how we need to avoid those, how we need to make sure that our wind turbines don't interfere with them. And then this is basically a cost matrix of these lease blocks and which ones are the most appealing to purchase for our wind farm design. So this lease block that we ended up purchasing, these circles are actually the just distances, the common distance away from turbines that are basically the accepted distance that you want to keep these things away from each other. You can actually see, if you look really closely, a little plume, and that is actually the expected wind flow from these turbines. So this is our turbine layout for the lease block that we decided to go with for competition. And actually we see an oil pipeline right here, and then right here the boundary of our lease block. And we have to actually do research in the turbines themselves. There's a whole wide array of turbines that are out there, and what turbines work best in the environment we're dealing with, where the winds are, at what altitude the winds are, generally in the environment we are at, how high we want our turbines to be, the length of the blades. All this stuff comes into play when designing these. Also, the anchoring system, whether we are can assemble our anchoring system on shore and then take it out and put it out into the ocean, or whether we have to build the anchoring system out there in the ocean and then assemble the wind turbine out in the ocean, and actually do the planning for how that would take place, how we would get the turbines in place, as well as how we would decommission them. And on top of that, doing wind analysis of the area and understanding just exactly how the wind can be typified for the area we're trying to set up a wind farm at. And then along with that, we have to set this up like a business and basically make a business proposal at competition to a bunch of people in industry who do this for a living. And they find holes in our design and they find holes in our financials analysis. And it's very difficult being engineers with very little financial background to set up a 20-year plan for a business and have it, go in the black and have not have any sort of holes in our setup. Fortunately, this year we have 2 electrical engineering students that also have minored in finance, so a little bit more experience this year in terms of setting that up. So these were kind of our 20-year finances. This is all very condensed and very. I'm giving you the very thumbnail, a very thumbnail sketch of these 20-year finances for this. But the main idea is that we're treating this as if we were actually going to build this, and we're presenting it to, say, like investors or whatnot. This year we may actually have to reach out to some of the grid people, the electrical companies in the Great Lakes, to find out what their capacity is for being able to accept renewables from another source, right? You have a capacity, your substations have a capacity for what they can accept from renewable sources outside of what they're generating. And we're worried that if we have certain turbines, we're going to be overshooting what they can actually accept. So we might have to reach out to a few of these electric companies and actually talk to them as if we were a real company considering doing this. So this next year we are doing this in the Great Lakes, and this makes for a very different situation, being that the wind is very much different than out in the ocean, and it's very deep. The water is very deep, and so it's not feasible to have an anchored system that you would see out in the ocean. So we're going to have some sort of floating buoy situation where we have buoys that are somehow anchored with tether lines to the floor of the lake, but it's going to be very different than our experience with the Gulf of Mexico. And another thing is there are no lease blocks. There are no defined lease blocks. So we are just open to put these things wherever we want, which is a plus on one side, but on another side, it's one of those situations where it's like when you have too many choices, it's almost like very daunting to find the right choice. And this part of the aspect of this is the environmental footprint. We have environmental engineers on our team that help us analyze the local wildlife, not only avian and aquatic, but algae, things like that, and what sort of things might this influence. In our Gulf of Mexico setup, we actually, one of the reasons why we went with a particular anchor that we did was that it was beneficial for coral to, they found in scientific studies that the coral actually attached to this certain anchor and used it as a home. So when these things are decommissioned and they take it away, it actually becomes like a home for the coral and everything. So trying to make our footprint as little as possible. So that is the wind turbine or the wind farm site design. And now finally I want to go through the final aspect of the competition, the community and industry engagement. This is a very broad category that encompasses not only engaging with our community and the university and Oklahoma in general, but also engaging with industry professionals and learning from them and making the connections with industry professionals. One of the major things that we are trying to do is grow the team. Our metrics, we're always tracking our metrics both in our social media posts and our people who join our various social media accounts, and our team growth and how big we're getting over a certain amount of time. This was all of last year, our team growth and our social media growth. We're also looking to metrics such as diversity and inclusion. We're trying really hard to broaden all of our demographics in our team. Currently, we're having a tough time with that. So any way we can get the word out, please help us out. So this is a flyer that we have out to try to get people interested on campus to join the Cyclone Cowboys. We are also this year talking about doing things like placing announcements on A-frames and even maybe putting a Cyclone Cowboys PSA on a highway sign, just to get people interested in wind energy and recruited to OSU Electrical Engineering Department, and who would be funding the highway sign and getting people interested in Cyclone Cowboys. So last year we did interviews with industry professionals, 4 industry professionals: Jamie McAlpine, who's a project manager for Chermac Energy Corporation; DJ Worth, who was a project developer for Ørsted at the time. He's since moved on to another company. Jared Beckstrom, a development manager for Apex Clean Energy; and Taiwoom Nam, a principal scientist for Toyota. And really interesting people to talk to, getting their stories on how they got involved in wind energy, what they're doing, and how their advice for how students can start getting a foothold into clean energy and wind energy in particular, and as well as the projects that they're working on. Taiwoom Nam is kind of he's kind of different from the other 3. These other 3 work in traditional wind turbines. Taiwoo was working on a project that was a tethering system with basically a balloon that would float into high altitudes, and then having a tethering system that would pull the balloon down and release it and generate energy from using that potential, right, from being so high up in the atmosphere. So very interesting stuff to be able to talk to them. Not only do we do that, but we do a lot of on-campus events, tabling events, trying to get our names out there, talking to people in the classroom, visiting introductory engineering courses, trying to get freshmen to join the student organization, and just basically attacking people on the street. Right, so a lot of on-campus events and then off-campus events as well. One of my favorite things that we did last year, and we're expanding it this year, is we went to Westwood Elementary and participated in their Gifted and Talented program. The teacher there, Miss Gray, had an idea for a program that tracked basically the developments in the book, The Boy Who Harnessed the Wind. And so she wanted to have the students read this book and then build their own turbines based on how the real person in this book built his turbine and helped his community with it. So she came to OSU and said, I don't have any background in this sort of stuff. I don't have any electrical knowledge. And she came to the electrical engineering department and she said, can you help us? And I saw this and I was like, this is perfect. It's like meant to be. So we jumped in and helped her design her curriculum for the technical aspects of that, as well as we came in with KidWin kits and did a design and build week where these students got to build these turbines and test them with fans and light up LEDs and design various different blade systems, multiple blades, shorter blades, longer blades, shaping the blades differently, angling the blades differently, and seeing what changes they made, how that would affect the power output and the LEDs that they lit up. So we're going to do more of that, more. We are going to, so far I have 4 elementaries signed up this year that we're going to go visit. Trying to get more, we'll see what happens. Not only that, Kathy Jackson has been instrumental in helping us spread out to the wider Oklahoma community. So this is us out at Tinkerfest at the Oklahoma Science Museum, about 10,000 people for that event that we were able to interact with and help build wind turbines on the spot. This was the grand opening of Engineering South and the station that we had there. So yeah, more of this. We are going to do Women in Science out at the Science Museum as well, a couple events in Tonquah, and possibly even set up a panel with industry professionals here on campus so that anybody can come and talk to people in industry about wind turbines and wind turbine design. And then to close this off, I just wanted to share these 3 pictures with you because they're my favorite pictures from that Westwood event. This girl encompasses my entire career in engineering. It's a lot of this first picture where you're just trying to figure stuff out and you're just consumed with it and you're just having a heck of a time getting something to work, and then something happens and you're like, oh, it worked. And then the joy from that experience is just, that encompasses everything that I love about engineering. So I wanted to end it there. If you have any questions, please let me know. Thank you all for attending online and in person. Thank you for coming. All right, I'm going to end it there.